Welcome to this video produced as part of the Further Maths Support Programme's material for A-Level Maths and Further Maths. This one focuses on work energy and power, and in particular on the work energy principle. Let's take a simple case: a body with a mass of m kilograms, a force F newtons in a straight line, constant, and a consequent uniform acceleration from u meters per second to v meters per second over a distance of s meters. If we consider just that force, what is the relationship between the force, the distance, the work, and the energy of the particle? Well, we'll see if we do some simple calculations. First of all, we know that F equals ma. There's our force diagram, and there's F equals ma, the basic Newtonian relationship between F and A. We also know from Suvat for constant acceleration that v squared is u squared plus 2as. Now if you put those two together by eliminating the a, that is to say make a equal to F over m, and substitute for the a in the second equation, we end up with the relationship at the bottom of the slide. Now that doesn't look particularly useful or informative at this stage, but if we divide by 2, strange thing to do perhaps, and multiply by m, we'll get rid of the 2 and the m there, and we'll end up with a half m in front of each of these two. So let's do that. There's the working again, the formula to be simplified, and I've ended up with that second line where it now begins to look suspiciously familiar. Fs sounds like work done. Half mu squared sounds like kinetic energy. Rearrange it and we end up saying that the work done is equal to the change in kinetic energy. Now in fact, when kinetic energy was introduced in this series, the formula came, as it were, out of a hat. You can now see why that formula is chosen to be a kinetic energy, what its significance is. That quantity is what's increased, if you take it in its generic form, is increased when work is done. Here, this simply states that the work done is the change, the increase in kinetic energy. Increase if we suppose that the work is positive, but generally that the work done is the change in kinetic energy, the final energy minus the initial energy. So we can summarize that by saying that the work done by forces, we've done a simple case with just one, but it generalizes. It also generalizes incidentally to forces which are variable, but that comes later. This is known then as the work energy principle. Work done is change in kinetic energy. Let's look at a simple case then now. We've got a force pulling a particle a distance of 5.5 millimeters across a smooth horizontal floor. The question says find the gain in kinetic energy. An interesting question because the question doesn't give us the mass of the particle. Presumably we can find it without knowing that. Well, we can if we use the work energy principle, because the work done by the force will give us the change in kinetic energy. So we have a force applied 4, and it travels a distance of 5.5 meters. So the distance, the work done will be 4 times 5.5, and that will be joules. So that's 22 joules. There we are. 22 joules is the gain in kinetic energy of the particle using the work energy principle. Now let's look at something a little bit more complex. A stone of mass 5 kilograms. It's sliding across a rough horizontal floor, initially at a speed of 4 meters per second, and then it comes to rest. Now we'll assume in this, as we'll see, that the forces acting are constant, and we'll relate energy and work as before. So first of all, let's calculate the change in kinetic energy of the stone. You've got a picture there which represents the kinematics, 4 meters per second to start with, 0 finally, and the distance travelled is 4. So the change in kinetic energy is the initial kinetic energy, which is half times 5 times 4 squared, minus the final kinetic energy is half times 5 times 0 squared. Now need to be careful here, because although that's the obvious way to calculate that, strictly speaking, the change in kinetic energy should be thought of as the initial kinetic energy minus the final kinetic energy. So really we should put that the other way round. So the final kinetic energy minus the initial kinetic energy is the change in kinetic energy, and that gives us a negative quantity, which is minus 40. Now see, be careful here that if you want a change and you want to relate it to the work energy principle, it has to be the final energy minus the initial energy, not, as it's temptingly put in this place, the other way around. This case, the other way around. So minus 40 is the work done. Very good. So how do we relate that to the force? Well, this slide is really to repeat those calculations. There we are, summarised. The change in kinetic energy is minus 40 joules. So it's a loss of 40 joules. Now, let's think about the work done by friction. The force diagram and the kinematic description are given there. This is the force diagram. The other diagram is simply to store the information in the question. Now, if we use the force diagram, then the work done is going to be minus F times 4, because the force is opposed to the direction of motion. And that equals the change in kinetic energy, which we calculated as minus 40 joules. So we can see from this that F is equal to 10. So the resistance force assumed constant, the friction force, is 10 newtons. So there we are, that's the answer finally. And notice it's crucial to have this minus F, because the force in my diagram was opposed to the direction of travel. So the friction force is 10 newtons. Well, that ends this video presentation. The next in this same series on work energy and power is about potential energy. I hope to be with you later to explore that.